Electrophilic additions to conjugated dienes. There's three words you probably weren't familiar with at the beginning of the semester. Electrophilic, conjugated, and dienes. Start at the end. Diene means an alkene that has two double bonds. Do you remember what it means if it's conjugated? You have two double bonds, or you can have two triple bonds, separated by one single bond. So if we look here at this reactant, we see a double bond, a single bond, and a double bond. That's what makes it a conjugated diene. It's a diene because it has two double bonds. Electrophilic addition means that the thing that's attacking is electrophilic. It is an electron lover. It is seeking electrons. All of these reactions, you can, if you want to personify things, you can think of them as they're fighting over the electrons. What are the electrons doing? Well, we see two different products if we add 1 mole of hydrogen bromide to 1 mole of 1,3-butadiene. We see a 3-bromo, 1-butene, and we see a 1-bromo, 2-butene. The first one is the result of an addition to the first and the second carbon. And the second product is an addition to the first and the fourth carbon. This first one makes sense. We've talked about adding things like this, and here the hydrogen is going to go to the carbon that has more hydrogens, and the bromine is going to go to the other carbon in the double bond. That's what we've learned about. That one makes sense. This one doesn't seem to make any sense. How are we adding a hydrogen to the carbon number 1 and the bromine is ending up at the other end of the molecule? That's not what we expect. And yet this happens a lot for conjugated systems. So we need to look at what's going on here. Well, the first step is that this proton is going to add to the terminal carbon. This proton is an electrophile. It's seeking electrons, and so the 2 electrons from this pi bond are going to come over here and form a sigma bond between the hydrogen and carbon. That's what we get right here. I'm sorry. This is the carbon. Now it has 3 hydrogens instead of 2. It's confusing how they drew that. Let me fix that. So that's a 2, and there's the hydrogen that we're adding. I think that makes a little more sense. I'll make this guy over here red too. So the pi bond electrons go over here to make a bond with the hydrogen. And we've got this hydrogen here. Because of that, the other carbon from the double bond becomes a carbocation, because it lost the electron that it was sharing with this other carbon. This carbocation is stabilized by resonance. Remember we talked about resonance? So here we have this molecule, and there's a positive charge here. But this double bond, the pi bond, could move over here, and the double bond can then be over here. So this double bond can move because those electrons can move back and forth. And so the carbocation can move over to the other end. Does that make sense? Does that seem weird? It's weird. I think it's weird. This pi bond, pair of electrons. Remember, electrons are attracted to positive charges, if that helps. Here you have a carbocation. These electrons can move over here. When they do that, this carbon no longer has a positive charge because it's got 4 bonds now. But the guy on the end is now short an electron. He's got two bonds with hydrogen and 1 with carbon, so he becomes the carbocation. Which of these carbocations is more stable, this one or that one?
The same, aren't they?
No, they're not, because remember we talked about primary, secondary, and tertiary carbocations, depending on how many carbon atoms are attached to the carbon with the positive charge. This carbon has 2 carbons attached to it. It has 2 friends to help it with its positive charge. This carbon only has 1 friend to help it. This is more reactive than this one is. This is resonance, and so these electrons actually do not jump back and forth, but they're actually delocalized and spread out over the 3 carbons. But the positive charge is more stable over here, and it's more reactive over there. So in the second step, here's our carbocation with the resonance, and the bromide adds, it's going to add where the carbocation is. So it can add to the second carbon right here, or it can add to the 4th, because due to resonance, the carbocation is also over here. And so we end up with 2 products instead of 1. That carbocation was an example of an allylic cation. An allylic cation has a carbon-carbon double bond that's adjacent to the positive carbon. So here's that carbon on the end with a positive charge. The next carbon over has a double bond. And these carbocations are more stable because of the resonance between them. And so when we look at an electron distribution map, we see that there's this positive charge is kind of spread out. It's not localized on one carbon or the other. So going back to look at this one, here's the carbocation. The next carbon over has a double bond. This is an allylic carbocation. Those are more stable than just a regular primary carbocation. So here's a problem from your book. Draw the contributors to the resonance hybrid structure of the 3-cyclopentenyl cation. So this is cyclopentene. It would get numbered 1, 2, 3. The cation, we're now specifying where the cation is. It's on carbon number 3. So what can happen to stabilize this? Is this an allylic cation? Yeah, it is. Here's the carbocation, the carbon with the charge on it, and if we go 1 carbon over, there's a carbon with a double bond. So what can these electrons do? They can move over here, right? 2-headed arrow means that they're both moving. And when that happens, now the double bond is over here. This carbon is no longer a cation, but this one is. Any questions? I think organic chemistry is a subject that you really, really have to work at understanding. It's not something that just hits you in the face. You have to work at it. And at this level, we really have to think about what are those electrons doing. Because rote memorization just doesn't work for most of this. So we've got resonance, the pi electrons, the electrons in the pi bond are going to move over here. They're trying to help out this positive ion. That's how I think of it. And so they move over here, and then the positive gets transferred to this side. And what this actually is resonance. and the carbocation is not localized on either of these, it's actually sort of distributed between both. But if we were going to add, what sort of a substance would add to the positive charge? A nucleophile or an electrophile? A nucleophile likes the nucleus, which has what kind of a charge? Positive charge. Here we have a carbocation. What's going to be attracted to that is a nucleophile. A nucleophile is something that has plenty of electrons. So it could be something like bromide. If this were the intermediate for adding hydrogen bromide, the hydrogen would add, and we get this carbocation, which can be stabilized, and now the bromide could add either at this carbon or at that carbon. Let's just draw a hypothetical. Where might this have all started? If we had a hydrogen add in here, and these two electrons come out here to make the bond. I'm sorry, I did that wrong. Need to put the hydrogen in the right place. The hydrogen down here. Electrons coming out to form a bond with it. And that would result in this carbocation being formed, because there's a hydrogen here now. The hydrogen added to this carbon, leaving a carbocation there. But that carbocation, because of this, it's an allylic carbocation, there's this double bond over here, that can move around. It can be on either 1 or 3, and so we can end up with the bromine on this carbon or on that carbon. Write an equation for the expected products of 1,2 addition and 1,4 addition of bromine to 1,3-butadiene. Well, we need to start out with 1,3-butadiene. We need the structure for that. So that comes from butane, which has how many carbons? 4. So we're going to have 4 carbons. The diene in the name tells us 2 double bonds. 1,3 tells us one of them is on the first carbon and one of them starts on the second carbon. So I'm going to number left to right. So there's a double bond between carbon 1 and 2, and then there's going to be a double bond between 3 and 4, and there must be a single bond in there. And then there's going to be H's. So this question is, I think it's kind. It comes out and tells us 1,2 addition and 1,4 addition. So adding HBr, a 1,2 addition would be to this carbon and this carbon, the 1 and the 2. Are these carbons identical? No. This carbon has 1 carbon and 1 hydrogen bonded to it. This carbon only has these 2 hydrogens overlooking this double bond here. So the hydrogen here, this is an unsymmetric reagent and this is an unsymmetric molecule. Where is the hydrogen going to go? To carbon 1 or to carbon 2? It's going to go to carbon 1 because it wants to go where it already has more friends. So it wants to go here because there's already 2 friends there. And over here, there's only 1 friend. And that's not a good scientific explanation for what's going on. But I remember it that way, and I think that's helpful. I'm just going to color code this H so we can see where he went. So 1,2 addition tells us that, what am I doing here? I'm zooming around, I got lost on my iPad. This molecule is going to add to the 1 and the 2 carbons. And the hydrogen is going to go to the one that has more hydrogens already. So it's going to go to this carbon, and the bromide is going to the other carbon. This is an example of 1,2 addition. They're adding to 1 and 2. Now what about 1,4 addition? Well, something is adding to carbon 1 and something's getting added to carbon 4. Let's think about what's going on in here. That hydrogen is going to go to the number 1 carbon. It's going to form a bond there, and then we're going to end up with a carbocation. All these tedious hydrogens. So there we've got a bond, and then this guy's positive. This is an allylic carbocation because on the neighboring carbon there's a double bond. This double bond can move over here, and we can end up with the carbocation on the 4th carbon. That's not the color I wanted. And the double carbocation. And then the double bond gets moved into there. All these hydrogens are staying in the same place. And we've got that red one that we added already. To get the 1,2 addition, the bromine added to this carbon. But because this can rearrange, there's resonance, and we can get the carbocation moving over here. The other product we get is with the bromine adding to the 4th carbon. Now, can you do that without thinking through the mechanism? Yeah, you can, but just be careful that you don't lose the second double bond. We're adding 1 HBr, and so only one of the double bonds goes away. The other double bond is still there, but it moved over. And that doesn't seem like it should be able to happen, but it does. So here's one product, the 1,4 addition, and this is the 1,2 addition. Any questions? Yes?
Why'd you take out the Br or the bromine on the 3rd step and you added a positive? How'd you do that?
Well, this one going this way, we just added it thinking about Markovnikov rules. But then to think about ending up with this product, we kind of had to go back and look at what was the intermediate. I don't know why it's doing that to me. I really didn't want it to do that. Now I lost the whole thing. Fabulous. Does that make sense? A little bit? Let's look at another type of addition to conjugated dienes. This is called a cycloaddition because it results in a cyclic product. We're going to look at our little friend here, 1,3-butadiene again. but here we're drawing him kind of hunched over. 4 carbons, double bond between the first and second and the third and fourth. And here we have ethylene, another alkene. So what can happen here is this pi bond can move over and form a bond between these 2 carbon atoms. This pi bond moves over here, this pi bond moves over there, and we end up with a cycloalkene. We've got 3 pi bonds that are converted, 1, 2, 3, that are converted into 2 sigma bonds and 1 new pi bond. And so the electrons have just done this little dance and made a cyclic compound. I will not ask you to do anything with this reaction on an exam. This is called the Diels-Alder reaction, and it's a really, really useful reaction for synthesis. It works better if we have electron withdrawing groups. So this is at a higher temperature, and this one will go at a lower temperature. These cyano groups, nitrogen is an electron, has a high electronegativity, so this tends to pull electron density away from this double bond. And here we've got all these groups that are pulling electron density away, and that makes this Diels-Alder reaction go much faster than without that. So draw the structure of the product of each of the following cycloaddition reactions. Let's skip this one. How's that sound? I'm just going to skip that one.